So in this section, we're going to talk about evaluating polynomial functions. We're going to define what a polynomial function is, and we are also going to talk about some of the behaviors of polynomial functions. Before we get into that, let's do a brief overview of what we will be covering vocabulary-wise and objective-wise. You'll notice that our objective today is to use mathematical symbols to represent quantitative relationships and situations. Talking about the vocabulary, we already said we're going to be dealing with polynomial functions. So our first vocabulary is simply a polynomial is a monomial or a sum of monomials. If you recall from Algebra 1, a monomial is defined as a single term. Usually it involves an x. It doesn't have to, but almost always it does unless it's a constant. Our second vocabulary term is a polynomial function is a function of the form which is listed below. It says f of x equals a sub n times x to the n power plus a sub n minus 1. And I know that this can be difficult to understand, but basically what they're saying is every function or every term that we have is going to have a coefficient in front of it, a number. If there's no number, then it's just 1. And then every exponent, it's basically we have different exponents. So like if this is to the 4th power, then the next one will be to the 3rd power, etc., all the way down. Now that doesn't mean that we have to have a term with every single power. It just says that's what the form is. And your a sub 0 will not equal 0. And all of the exponents have to be whole numbers, which means they have to be 0 or higher. 0, 1, 2, 3, 4, 5, and they have to be real numbers. So that's the definition there. This next one, this is going to be an interesting concept that you may not be familiar with. It's called synthetic substitution. And synthetic substitution is just a way to evaluate a polynomial function that involves fewer operations than direct substitution. So your substitution that you've usually done is just take a number, you substitute it in for the x value into your calculator, things like that, and then you get an answer. Synthetic substitution is a way to do it without doing it that longer way or using a calculator, and you'll kind of see that. And the last thing we're going to talk about is end behavior. And this is going to be a new concept for you, but it's a very important concept, especially moving on to calculus. And an end behavior is basically just describing what the behavior of a graph is as you approach positive infinity on the x-axis or negative infinity. So let's just get to this. We're going to go through these one at a time. We already talked about what a polynomial is. And remember, the whole numbers are 0, 1, 2, 3, etc. And real numbers do not involve I, meaning they're real numbers, they're not imaginary numbers. Okay, so the few things that we need to talk about is we need to know what a leading coefficient is, what a degree is, and what a constant term is. So the leading coefficient is going to be the number or the coefficient that's in front of our highest power. So if your highest power is the 4th power, the leading coefficient will be the number that's in front of that x term. So in this first one right here, we have 5x to the 3rd minus 2x squared plus 10x minus 15. Well, our highest power here is 3. Therefore, our leading coefficient is going to be 5. The next thing we talk about is degree. Degree is just simply what the highest power is. So because to the 3rd power is our highest power, the degree is just going to be 3. And then our constant term is the term that we have that has no x with it. That's what we call a constant, is something that will not change. So the constant term here is negative 15. Don't forget that negative in front of it. So below here, with these 4 problems, I would like you to decide whether each of these are a polynomial function. So what you can do is pause your video, and then I will come back, of course, when you hit start, and you will know whether you got these right. But try these on your own real quickly. So go ahead and pause right now. Okay, so looking at this first one, we have to decide whether this is a polynomial function. This one is a polynomial function, and the reason is because everything lines up exactly the way we need. We're allowed to have fractions here. We have a real number and a whole number as our exponent, and then we have our constant at the end. Our second one, this is going to be no. And the reason is we cannot have negative exponents. That is not a whole number. A whole number does not involve negative numbers. Our third one is also no, because we have an exponent as a variable, and that cannot happen in a polynomial. And then the last one, this could be a little bit confusing, but this is yes. Even though it's just 0.25x, there's nothing in here that tells us this is not a polynomial. Our exponent is 1, even though it's not shown, it's 1. Our coefficient is just a decimal, is a fraction, so that is a polynomial. Okay, so now what we're going to do is we're going to talk about this idea of synthetic substitution. So this is a different way to do it. This doesn't mean that you have to do it this way, but I would like you to practice this. You may find that this is actually pretty simple. As you saw from some of the problems we were doing from chapters 1 through 4 in those assessments, a lot of you were struggling with substituting in and knowing what to do there. So maybe this synthetic substitution will help you. But let's just go through this real quick. Basically what you're going to do is you are going to set up a kind of a graph or a table that looks like this. On the outside will be the x value that they're giving you. So it says x is equal to 3, so that's why we put a 3 on the outside here. On the inside, what you're going to do is you're going to put the coefficients, or the numbers in front of each of them, in order from largest exponent down to smallest. So x to the fourth is our highest, so therefore we put 2. Then x to the third, so we put -5. Don't forget this negative, that includes it. Okay, the reason why we have a 0 here is because we don't have an x squared term. So you need to make sure that if you're missing a term that you put a 0 in there for that. Then we have -4 and then 8. So here's how this process works. Our first step is to bring down our value. So we bring down our value 2. So the 2 comes straight down. Then what we do is we take the x value that they gave us and we multiply it by the bottom number. So 3 times 2 is 6, so we write 6 right here. Then we just simply add these two numbers up. -5 plus 6 is 1. And then we just continue the process. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. 3 times 9, or sorry, -4 plus 9 is 5. 3 times 5 is 15. 8 plus 15 is 23. Therefore, our answer when we evaluate is going to be 23. And you can see all the work is done below what I just put up here. So therefore, f of 3, and remember, this just means f of whatever they're giving you your value of x, which is 3. That's where we got the 3 from. That's what this notation means. F of x when x is equal to 3 equals 23. So let's do a couple of examples below, and then you'll do one on your own. Actually, you'll do 2 on your own. So let's go through this. So x is 2, so we're going to put a 2 here. We start putting our coefficients. -3, +1, -12, and -5. We bring straight down our -3. 2 times -3 is -6. 1 plus -6 is -5. 2 times -5 is -10. -12 plus -10 is -22. 2 times -22 is -44. And -5 plus -44 is -49. So therefore, f of 2 is going to equal -49. And what that means is that if you were to actually take this x equals 2 and plug it in for your x values and do 2 to the third power times -3, etc., all the way through, you will actually get an answer of -49. This is just maybe a quicker way of doing it, a different way of doing it, not necessarily quicker all the time. Okay, let's look at the next one. Give you a second example here. So x is equal to 4, and we have -8. And now we're missing our x squared term, so we have to put a 0 there. Then we put 14, and then -35. Remember, don't forget your negatives. So going through this quickly, bring down the -8. 4 times -8 is -32. 0 plus -32 is -32. 4 times -32 is -128. So 14 plus -128 is -114. 4 times -114 is negative 456. Negative 35 plus negative 456 is negative 491. So therefore we have h of 4 is equal to negative 491. So what I want you to do is try these bottom two on your own and then come back and see if you get the right answers. So I'm not going to go through the entire examples to save a little bit of time. So I just want you to do these on your own and see if you come up with the right answer. So pause the video right now, try them, and let's see what you get. Okay, we're back. So hopefully you tried these on your own. What you see from this one is we found that f of 2 is equal to 76. If you got this wrong, one of the things you want to make sure is that you put it in order of decreasing power. So the 5 was in front of the x to the 4th, and then the negative 1 was in front of the x to the 3rd, negative 3 in front of the x squared, 8 in front of the x, and then we didn't have a constant. So don't forget that you have to have a 0 there. So that may have been the mistake there. This one was a little bit more straightforward. The only thing is maybe you forgot the 0 right here. But other than that, you should have gotten h of 5 equals 645. The last thing we're going to talk about is end behavior. And this is a commonly confused topic, but it's actually fairly simple if you're paying attention to what a graph is doing. The end behavior is just simply what is happening to a graph as x increases. So as you go to the right or go to the left. Okay, so what we're going to do is go through these key concepts real quick. So the end behavior of polynomial functions. The first thing is if you have a degree that is odd. Degree is odd, which means the leading power is going to be an odd number. So 1, 3, 5, 7, etc. And the leading coefficient is positive. If this is the case, this is the type of graph you typically get. And this is what's going to follow. As f of x approaches, as x approaches positive infinity, your f of x is going to increase to infinity. And as x goes to the left or goes to negative infinity, your f of x is going to be negative infinity. Okay, the opposite is true. If your degree is still odd, but your leading coefficient is negative, the complete opposite is true. As x increases towards infinity, your f of x will be negative infinity. And as x increases or decreases to negative infinity, your f of x will be positive infinity. Now it's a little bit different when we get to the even functions. Even functions, you notice, will go in the same direction. So if we have a degree that's even, and we have a leading coefficient that is positive, then what you'll notice is no matter whether we're going towards positive infinity to the x or negative infinity to the x, your f of x always goes up to infinity. And then the complete opposite is true if our leading coefficient is negative. No matter where we go, if we go to positive infinity or negative infinity on the x-axis, we're going to be going to negative infinity as our y. So remember, end behavior is just simply what is the y doing as x approaches positive infinity or negative infinity. Okay, what I want you to do here is, what do you notice about the end behavior of odd functions? What do you notice about the end behavior of even functions? I'm not going to give you the answer to this. I want you to just write it down and we'll talk about it tomorrow. Okay, down below, let's look at these examples. So we have f of x equals 10x to the 4th. Now, we could easily memorize this up here if we wanted to, but I'd rather you not do that. I want you to think about what an even type function, what type of function it looks like. And what you'll learn real quickly is it typically looks like a parabola. So that means it's either going to go both up or they're going to go both down. So here, we know that it's even. We know that this is positive, so it's going to open up. Remember, positive means opens up. So right away, you could say f of x is going to go to infinity for both of them. The second one, again, we have an even function, so we know it's a parabolic type function, but the front is negative, which means it's going to open down, so both of these would be negative infinity. Okay, and then below we have two odd functions, and odd functions, those are the harder ones to remember, but we have an odd function that's going to look like an x to the 3rd function with a negative coefficient. So you look at your chart, and you will see that as x goes to negative infinity, it'll be positive infinity, f of x will be, which means the other one's negative. And then over here, it's completely the opposite. Because our coefficient is positive, it's going to go to negative infinity, and then positive infinity. And that's it. So we'll see you tomorrow.